What if a perfectly patched industrial machine can still hide vulnerability where usually no one is looking? And what if the programming languages that are used to write the automation logic of these industrial machines are so powerful to allow, for example, a threat actor to implement malware and hide that malware into the automation logic itself? To answer these two questions, we have to go back about 2 years ago when this research started. It started from an app store, but not the app store that you have in mind. It was an app store used to distribute code meant to run on industrial machines like this one. So an industrial app store. So we started to download some apps because this looked very interesting to us. And we reverse engineered some of them to see how they were implemented and the languages and so on. And one of them was particularly interesting because it was a simple web server. Yes, a web server running on one of these industrial machines. We installed it on a simulated factory environment, such as the one that you see on the lower part of the screen, and we started to use it. This is what we saw when we connected to it using a regular web browser. So it's a classic example of a status page, right? That you can see, for example, the status of the motors, and you could even download some files from the root of the web server, not the root of the machine, of course. So we spent some time looking at the code. As you can see, the code is not very complicated to understand, although the syntax might look a little bit different from the languages that you're used to. Not too complicated. It's a rather simple grammar. And after looking around for a while, we found something that you might have spotted already if, for example, if you are a web developer or if you have done security assessments on web applications. Yes, it's a path traversal vulnerability, which is a classic vulnerability found in web applications that may allow an attacker to exfiltrate files that are outside of the root directory of the web server. So it was quite interesting finding, because if an attacker is on our network, they could exfiltrate whatever is inside the robot. So we wanted to test it, and we implemented a simple exploit. We prepared a file outside of the root directory that we wanted, our target file that we wanted to exfiltrate. And in the second box, you can see the secrets.txt file. And using a crafted web request with enough slashes, we were able to exfiltrate the list of files and even the content of the files. Looking back at the code again, we found an interesting comment left by the original developer, saying that browsers will remove the /... from a top-level request, which means that the developer is trusting that the browser will do the validation. While we know that this is not a very secure coding practice, because it's essentially assuming that an attacker won't be available, won't be on the network, and won't be capable of crafting such requests. While we have just demonstrated at least that it's simple to craft such web requests in order to exfiltrate the files. The story that you just heard is what motivated my colleagues and myself to start digging deeper into this space. My name is Federico Maggi. I'm a researcher with Trend Micro Research. And if you're curious to know how this story ends, let's keep watching. Of course, we reported the vulnerability to ABB, and the ABB responded to the quote given by Bloomberg that they have removed all the issues that we have reported. It wasn't only this issue, and that our actions, our reports, help them to provide a greater security for their products in the market. The first thing that we learned from looking at these apps is that the languages are different. They're definitely not mainstream languages such as Java, C, or Python, right? And each vendor has its own proprietary language. We looked at 8 of the major vendors, such as ABB, KUKA, Kawasaki, Mitsubishi, Komau, Denso, Universal Robots, and Fanuc. And we found out that they're all different. They seem to have all the interest in retaining their existing customer base, because it's very anti-economical to switch from one platform to another, because the ecosystem, the development environment is completely different and they're not interoperable. These languages are almost entirely focused on expressing mechanical movements. In the example here, you see the definition of 2 points and A and B, and a program that loops between those 2 points. So you would see the robot arm doing back and forth continuously for 10 times. What actually caught our attention is that these languages go beyond these movements instructions. They have, for example, capabilities to handle files in a programmatic way. So you can write a program that reads and writes files. And you can write a program that at the application level talks to the network directly. It's quite understandable because, as we said at the beginning, they are not interoperable. So having a network connection makes them more connected. So you can write programs that talk to network daemons, for example. But the most surprising finding is when we found that most of these languages allow to load and run code at runtime. New code, I mean. So that means that a developer can write a program that connects to the network, fetches another file, loads that file as code, and jumps to that code while an existing program is running. From the perspective of a vulnerability researcher or an exploit developer, this is gold, because it's a writable and executable memory area. You can do whatever you want given this primitive. So the question is, are there other classes, other types of vulnerabilities that we have found? I think the most frequent case was what we called into motion servers. Motion servers are essentially network services that expose a simple API, usually through UDP, but also TCP. And they allow to listen for commands, movement commands, that's why they're called motion servers, to receive movement commands from the outside, and the robot will essentially execute those movements only. I think the ROS project is the one where we found most of the motion servers. And it makes sense because the robot operating system is the largest open source operating system for robotics. It's also used in production, not only in the industrial field, but also in consumer robotics, including in cars and the home robots. And the motion servers are a way to expose a uniform API to an otherwise completely fragmented technology. Because as we said at the beginning, each platform has its own language, its own primitives, and so on. So exposing a common API allows the users of ROS to talk to any robots vendors using a common language. What we found out in public code written for ROS is that there's no input validation in the motion server, which means that if the attacker is on the network, they can send any data to these API and the API will interpret it. Or the API can accept movement commands which are outside of the limits of the robot. That's why it's very important, if you're running a robot, that you have a safety system not only installed, but configured correctly. For example, in our lab, we simulated a misconfigured safety system and we launched an exploit against this vulnerability. And we were able to hit the border of the cage of the robot so hard that the safety system did not engage fast enough that the robot arm fell on the floor. and we had to send the robot to maintenance. So this example is to say that if there is a possibility to implement input validation, it is important to implement it everywhere, not just on the safety system, not just on the input of this network API, on both of them, and they should be consistent. It's pretty much like when you develop a web application. You want to implement input validation on the client side because you want to make the application usable. But you must implement the same validation, if not stricter, on the server side in order to avoid ingesting incorrect data. With input validation, even if the safety system is not perfectly configured, we can avoid most of the problems because we can disregard any invalid coordinate. Here's an example of a motion server. As you can see, it interprets 6 real numbers from a network packet and then gives those as coordinates to the PTP to the PTP command, which is the point-to-point instruction, telling the robot to go to that point. Of course, we disclosed this vulnerability, and the people at Ross Industrial Consortium released a very practical and useful guideline that I highly recommend you to read if you want to configure your robot in a correct way in order to avoid the exploitation of this vulnerability. Even if the vulnerability is still there, if you implement the guidelines that are listed there, then it's quite safe for your deployment. There is also an ICS cert that was released after we reported the finding, which contains further details. So if you're curious, just go and look up this alert. Another class of vulnerability that we found is input validation on function calls. If there is an automation code that implements function calling with a dispatching routine that is based on external data or attacker controlled data, that means that the attacker can influence what function will be called. For example, we found this code in a public repository of a university, and now it's been taken offline, where you can see that the program fetches data from the network and then uses that data to calculate a string, and that string is the function name, the name of the function to be called. But it doesn't perform any validation of whether this function is allowed to be called, even if this function is existing in the code. So for once, the attacker is able to disrupt the execution of the program, but he or she may also be able to call arbitrary functions that are already defined in the code, which are not meant to be run. Instead, with input validation, having a whitelist of the functions that are meant to run, these things won't happen. Again, this sounds all basic maybe if you are a web developer that knows all of the secure coding practices, but it looks like in this space, programmers are still thinking into a closed world assumption that no attacker will ever be on the network able to send arbitrary data to these network APIs. Another question is, have we found anything else beyond these vulnerabilities? I want to tell you something about the runtime environment of these operating systems. The programs that I just showed you, the automation logic, run on a in a user space where the kernel does not perform fine-grained process isolation and resource isolation like it happens in modern operating systems. If you take, for example, mobile operating systems, which, yes, are like 20 years far in the evolution, essentially, timeline, all the apps are sandboxed, and every app has to declare and request permissions to access other resources or resources that are on the hardware of your phone. So if your app wants to access the camera, they have to have the permission, and the user has to grant that permission. To our knowledge, there isn't something like this implemented on these robotics operating systems. So if there is a malicious app, then that app will be able to access any resource and, for example, the disk or the network and so on. So the next question that you might have is, can we write malware? Given these premises, can we write malware in such languages? Well, let's see. We can load and send data via network. So it means that we can scan the network for targets. We can jump to code that is available at runtime. That means that we can implement a dropper. So let's see. Yes, we can scan the network for targets. We have implemented a simple proof of concept here. We scan as a number of IPs on certain ports, for example, because we know that those ports are running behind those ports there is a network daemons that is vulnerable, right? Here is a generic malware dropper if you're interested. It's essentially a network loop that consumes data from a socket and then writes that data onto a file and puts that file in execution. Can we exfiltrate files? Yes, we can exfiltrate files because we are allowed to read files from directories even outside our scope, and we can send them out via network. So I think it looks like we have all of the ingredients, and I think it's a good time to take a look at a quick demonstration. Here you see 3 robot systems. One of them is already infected and connected to the network under the control of the attacker. The other 2 robots you can see here are not infected. This is robot number 2 from the left, and this is robot number 3. But they are running a vulnerable version of this logic. But only one of them is connected to the network. So the attacker now tells the first robot, which is infected, so it's essentially a bot, to start scanning the internal network for targets. And as you can see, it found 2 targets already, which are both vulnerable. We limited, of course, the number of IPs because we wanted to keep it short and fast. And now the attacker can launch a propagation command, which is essentially instructing the first malware to propagate to any target found on the same network. As you can see, the robots can still running. They can keep doing their task. Here, for example, they're doing a collaborative pick and place task. And you don't see any disruption in their movements. But when this cycle ended, as you can see, the propagation has finished. Now let's go and see what's the status of the 2 files that we've looked earlier. Now we are on the second robot. It's now infected, which means that the propagation has happened. And so is the third one. So let me switch back here. So now you might be asking, show me some vectors. Show me how the attacker is able to get onto the robot in order to plant this malware or to exploit the vulnerabilities that I explained you earlier. And we're back to app stores. App stores are a very interesting indirect attack vector, as well as a place where I think most of the security measures could be implemented in the future. Essentially, as it happened for mobile application stores. At the beginning, you remember there was a lot of malware. There was very frequent to find malware on app stores, but over time they've gotten better and better, and now it's something very rare to find. So it's a very good opportunity, I think, for the security industry and for the industrial automation industry to invest into app store security, because I think that in the future, app store for industrial software will be not the primary, but a very common way to distribute software for industrial applications, because industrial applications are going to be more and more common. So among all the app stores, we looked at ABB App Store, which is probably the most, I think the most advanced one. It's similar to the App Store model that you may have encountered. So it's like your mobile app store, and it's like it works as an app store in the sense that developers can upload code. Then somebody is supposed to inspect that code and then give approval or not. After looking at the ABB App Store, we found a vulnerability by which we could upload an app, as you can see there, and when the app was pending for approval, it was still possible, even during this approval window, to immediately install that app right from within the software that usually is called the OLP software that is used to program the robots. So basically we have an indirect path going from the attacker machine to the App Store, down to the engineering workstation where the code is usually developed, or where these apps are consumed and used, and then down to the robot machine. We went one step further because we wanted to see if there was any human in the loop, if there was any validation of the code uploaded, right? So that pending validation bug was something that was fixed very quickly and easy from ABB. We wanted to see how the process was. So we uploaded a perfectly benign and safe application, but whenever you run it, if you run this application, you would see a very clear pop-up saying, hey, this application is not meant to run to be considered, it's only for research purposes. Please do not disregard it. If you install it, just remove it. We just wanted to see if there was anyone taking a look at the applications that we uploaded. And yes, this application got approved. Nobody has even tried to run this application to see what was doing, and it was approved right away. So yes, it also was downloaded a few times. We don't know by whom, but fortunately this app was only a benign one. Imagine if, this experiment tells us, imagine if there is an attacker who wants to exploit the lack of checks in the process. They could easily upload code indirectly onto the engineering workstation used to program a robot. Now I think it's time to wrap up a little bit and see what remediation approaches we can adopt in the future. We want to call the attention of automation engineers, system integrators, and OEMs. And we want to divide the approaches into existing deployments, new deployments, future deployments. Future deployments mean the next generation of robots. I think that network segmentation is something that we can immediately implement, even on existing installation and deployments, without very long downtimes if it's planned correctly. After our disclosure, as I anticipated earlier, the Rossi Industrial Consortium published a practical guideline showing how to properly configure the network to mitigate attacks against the vulnerabilities that we disclosed. By the way, the setup shown on the left is the correct one. In our paper, we describe how to write, we give a practical guideline meant for OT folks, showing how to write secure code for industrial automation. If you think in terms of development, this is something that a web developer, for instance, is used to know over the years. But now I think that the same principles, the same concepts of secure code development should be ported into the OT space, because more and more development will happen in the future. To catch vulnerabilities and malicious patterns like the ones that we found, we also have developed a system that is capable of automatically scanning the code and spot if there is a vulnerability or a potentially malicious pattern. And this can be applied to both existing and future development, because it doesn't interfere with the operation. It's something that you do before deploying a new program. So it's just an intermediate steps. I just briefly go through it to give an idea of how it works. Essentially, we divide a program into sensitive sources and sensitive sinks. And whenever the scanner finds a path from a sensitive source, such as a network socket, to a sensitive sink, for example, a movement command, then it means that an attacker on the network can influence the movements. And we go through a series of steps. I won't go into details here, from parsing to constructing the CFG, the ICFG, and then data flow that allows us to make queries and say, hey, I want to know all the paths that go from this source, for example, which is the interface, network interface, to this sink, which is the movement command. Right? Marcello, who is our research collaborator, has presented all the details of this at the Asia CCS conference. So if you're interested, check out the Asia CCS conference website, where they have the recordings as well as the papers. And last, I think that the OEMs can really make a difference here, in the sense that they are responsible for the next generation, for the security of the next generation of robots. And I think that together with, in the shorter terms, together with system integrators, they could start developing adapter libraries, like libraries that implement features that are not yet available into languages that are used right now. For example, security libraries for string sanitization, to implement strong encryption and authentication. So something that is currently lacking in those languages. And in the longer run, they should consider to implement fine-grained privilege separation and code signing to prevent unwanted code to run on a machine. To conclude, it feels like going back about 20 years ago, when the first web applications were opened to the public web, and they were already vulnerable, but nobody cared about that because they were just closed web application. But with a public-facing web application, even a simple vulnerability such as a path traversal becomes quite important. The second thing that we'll learn is that even if I sound like a broken record, there's no resource isolation, which means that if bad things happen, they can be very bad, because a malicious program can access all of the system resources. So please, we ask automation engineers to start considering security guidelines such as the one that we have published. And CISOs, please consider proprietary languages into your auditings. We have a working prototype, so if you're interested, get in touch with us. Whereas if you want to look at the details, take note of those 2 URLs where you can find all the papers. Thank you very much for following. Bye-bye.